Okay, tonight, as you've seen flash by on the screens, most of us are familiar with LFP batteries. I happen to have a 100 amp hour battery myself. I run my 2 meter rig off of it. I charge it about once every 3 to 4 months. And I've got a little Yaesu that runs about 60 watts. Seems to do quite well with it. But tonight, Greg, KO6TH, is going to be talking to us about the do's and the don'ts and what is good to do, what is probably not so good to do, and how to live well with your battery.
What started all this was some discussions back on groups.io. There was about battery charging, and I did this, and this is working and stuff. And yeah, all that stuff was true, but it wasn't getting to the point of kind of what was going on underneath. And I thought we ought to set a foundation of understanding on how these things work. Not so much how to do things, but why we do those things. You can build whatever solution you want on top of it, but to understand what's happening under the covers. So I'm going to talk about lithium iron phosphate. LFP is the abbreviation most people use, and kind of do a little bit of myth busting and unmarketing because there's a lot of that going on. Marketing emphasized to a lead acid world. This feels a lot like selling a new EV by saying, hey, you don't have to buy A anymore, and the shoes last 6 months instead of 3. It doesn't help you with understanding what lithium is all about. It's better compared to lead. It's better capacity, longevity, weight, size. Everything's wonderful. Same voltages. You got thousands of cycles instead of hundreds, maybe even hundreds. It can sink a lot of current, so it's more efficient on charging. It can source a lot of current with no lag, sag, no voltage sag. So what's not to like? All this stuff is true, but the details are where things get kind of squirrely. Lithium iron phosphate, all lithium batteries have a much narrower temperature range than lead acid. Lead acid, if you're living up in the Klondike, you can start your car usually, big enough battery, but lead or the lithium, it's not going to like that. You can't charge lithium below freezing. Period. This isn't like you get away with it for a little bit. Chemical changes happen to the battery below freezing, and bad things can happen. You can connect batteries, lead acid, regular flashlight batteries, series and parallel, and all kinds of stuff. People do that all the time. Read the instructions of the stuff on your lithium iron. Some of them you can't connect them in series. If you want 48 volts, you don't put 4 of them in series necessarily. It depends on the brand. Some of them have them limited on the number of you can put them in parallel, usually 4. Some you can do 16. Can you do 30? Probably not. There's things when you try to charge them with an alternator that you can fry the alternator. Oop, that's not going to be good. They're getting better at starting engines. There's special versions of the LFP batteries that are advertised for engine start. Most of them aren't. Some of them do. But the ones that do, you can do that. They still claim this is all drop-in replacement, but drop-in is not exactly the right thing. To look at some of these things, this is kind of these things everybody does. We all do these things until we can't. We get away with it until we don't. And there's a couple of different areas. I'm going to go through these in sequence, not in sequence, but go through all the points. In terms of charging and the concept of float, they kind of work together. Some background on how lead acid works. You start putting current in this thing, you want to limit the current, but generally the battery will start limiting the current for you. It's got a lot of resistance internally. Till you get up to 14, 15 volts, somewhere up in there. It's not critical. You push the voltage up, then you hold it there for absorption, let all the juice absorb into the battery until the current's going to drop. And when it drops down about 3 or 5% capacity, you're done charging. The battery's charged, but now you got to have maintenance on it, called the float phase. And basically what you do is you put 13.8 volts on this thing, magic number. That's enough voltage to keep bad things from happening. It keeps the battery charged. It prevents it's called sulfation. It's not so high as to start decomposing water into hydrogen and oxygen, which can do bad things. So it's a little range there, above about 13, 13.8, somewhere up in there, does that. And there's also a fourth phase. Yes, there's this equalization, but that's kind of a special case. We don't need to worry about it. So that's what lead acid does. You throw a lithium battery into that environment, and now, I mean, it kind of works. Bulk charge, that first phase, right? The voltage curve on a lithium battery is really flat. Lithium iron phosphate specifically, really flat. So for most of it, you're not going to see the voltage changing. And you're saying, what's going on with my charge percentage? Don't worry about it. It's cosmetic. When it gets through the charge phase, the voltage goes up. It stops charging or stops that phase, the bulk charge phase. But be careful. Lead acid batteries aren't very fussy about the voltage. Lithium is. If you get above 14.4, some strange things happen, and the BMS, the management system, can say whoop and do a disconnect. Now, some people think of that as being, okay, my battery's charged. No, it just means you got above 14.6, is what it ends up being. And the BMS entered into it and said, nope, you're done. Battery's not charged yet, but you're done. Side effect of that is your alternator sitting there putting out 90 amps. And all of a sudden, there's no load. What happens to an inductor when you remove the load from it? You get a huge voltage spike. And there go all the rectifiers, the diodes in the alternator, and anything that's downstream of that is going to get fried in about a millisecond. And that's not good. So yeah, you can use a lead charger with a lithium battery if you watch those voltages. And then there's this float phase at the end where it goes to 13.8. 13.8 is a magic number for lead acid batteries. It's also a magic number for lithium for a very different reason. But 13.8 is not the voltage that a lithium battery will want to sit at. It wants to sit at about 13.2 to 13.4. Because if you keep on putting 13.8 into it, it's going to keep charging. The BMS is not going to do a voltage-dependent interruption, and you're going to overcharge your cells. It'll take a little while, but you're going to ruin your battery. So if you can't adjust the float voltage on your charger, disconnect the battery. Then you can get by with it. Charging with an alternator, I touched on that a second ago. There's this wonderful thing about lithium, they can sink a lot of current. Very efficient for charging, but alternators typically are not designed to handle a lot of current for a long period of time. They depend on that battery coming up in voltage, current comes down, the little fans that are inside start dissipating the heat, and they're okay. If you have a huge, lithium batteries are way bigger in capacity than a lead battery. The alternator is not going to be happy with that, especially at idle. It's not spinning very fast. And then there's that disconnect we talked about that you can do you can fry the diodes. Yeah, so you got to be careful. You can use an alternator, but you need one that's designed for that kind of environment. Usually what you do is you charge a lead battery and then do a DC to DC from the lead to the lithium, or get a specialized charger that's designed for that. Engine starting, not a big use case. They're advertising it because, hey, we're drop-in replacements, right? Most lithium batteries don't include a cold cranking amps spec on them. If they do, look at that, look at your motor, see if they're compatible. If you are, great. If you're not a good idea to use it that way. Especially in cold climates. Now, all batteries, lithium and lead acid, lose capacity when it gets cold. But when it's really cold, you can't charge the lithium battery. So you charge your car, great, minus 20 degrees or something. It'll run. And then you go and charge back up again. So the next time you're going to start it, it ain't going to be there. Voltage measurement as a proxy for state of charge. If you look at, this is a not exact curve, but a representative curve of charging a lead acid battery. The voltage goes up pretty linearly until you're done charging. And there's several volts range between empty and full. You can kind of get a pretty good idea where you are on that curve. With a lithium battery, you put your meter on, hey, I got 13 volts, I'm good. No, because you're right at the edge of being empty. It's hard to tell. It's a very flat curve. Like half a volt between empty and full. It's ridiculous. It's great, but you don't need a regulator on it anymore because it's got a flat curve, but you can't tell the state of charge just by looking at the voltage. You got to count the electrons going in and out, and they got devices that can do that. The BMS is a big topic of discussion. There's three functions in a BMS. There's safety, there's balancing the cells, and there's some added value of connecting to the outside world. Safety is, which is what it says. It's not to protect the longevity of the battery so much, it's to keep it from blowing up. If you go above 3.45 volts per cell, 3.65 volts per cell, bad things happen to the lithium iron phosphate battery. Below about 2.5 volts, 2.2, 2.3, somewhere down in there, there's a chemical change that happens inside the cell that grows little dendrites and things that can short the battery out. And if you've ever had your laptop suddenly not take a charge, it's probably because laptop batteries, they have like 3 cells in series. There's no balancing between them. One of those cells got a little lower than the other ones. And as the laptop drained them down, that one cell got reverse charged a little bit. Now, nickel cadmium, who cares? Lead acid, who cares? Lithium, you care. Because all of a sudden, that cell has gone below its minimum. There's a little chip inside that battery. It's not a full-scale BMS thing. A little tiny chip inside the battery is watching the voltage. And when that voltage gets below that critical level, it disconnects the battery permanently. You can't go back in there and jump start it. It's dead. So if there's a disconnect, if the EMS does a safety disconnect, it's a serious deal. It's not casual, not an end of charge, oh, it's too low today kind of deal. It's important. The cell balancing is a longevity thing. It's trying to keep all the cells within, we're talking millivolts. The BMS I have at home, I've set at 10 millivolts is the level of criteria for being balanced. Besides your laptop, your Makita drill, your Ryobi, with all those things, lithium power, those don't have balancing either, I found out. The discussion on Hackaday recently. That, yeah, they discovered there's got a BMS in it. The balancing is not enabled. So when the battery goes dead, it's because it was probably because it went out of balance. There's a temperature check on that's active safety is the temperature and the current. Oh, the current. Short circuit detect. Has anybody dropped and lived a wrench across a lead acid battery and lived? Okay, big things happen when you do that. If you drop a wrench across a lithium iron phosphate battery, it bounces off and you almost think nothing happened. And what happened was the BMS in there detected the short circuit and turned it off instantly. You know, the fuse didn't even have a chance to blow. And so people are really scared about lithium batteries being, oh my God, they're so powerful. Yeah, they are, but they're also a whole lot safer because of things like that. The last function is communication, external stuff. People look at it with your cell phone. You can see how your cells are doing, get the charge, all that kind of stuff. You can see what's going on, but it's got a bit bigger function down the road here. A little more detail on the balancing. I mentioned 13.8 on a 4-cell battery. That's an important number for a lithium iron phosphate battery as well, not for the same reason. Got nothing to do with floating. What it is that's the part of the curve, the charge curve, where a BMS can tell how much the capacity is, what the state of charge really is on that cell. In that flat region, it's so flat, there's no clue as to what the actual state of charge is. So you got to push the battery up into that hockey stick in order to balance the cells. Don't go too high, above that 3.65 per cell, but above 3.45, which happens to be for 4 cells, happens to be 13.8. Don't get confused, it's a different 13.8. And once you get it up into that region, hold it there, let the cells balance, the current will drop, and now you're absorbed and done, fully charged, everything's wonderful. And at that point, if you want to drop it back down into that flatline region, float, if you will, basically don't have any more current go into the battery. And if you want to you know, use it as like a UPS. You can drive your loads with like a power supply, but only at 13.2, 13.3, somewhere in there. You can't go up to 13.8. You can't use the float. So BMS, bottom line, is not a charger. Let's look inside, understand why not. BMS, you got control logic, you got temperature probes, you got even a heating pad. You got wires that don't show up in this diagram for some reason, but on YouTube you'll see them. The wires between the control logic and the batteries and the current sets, and some FETs to turn on and off the charging and discharging. The reason you can't use the BMS as a charge controller to regulate charging is that it's on and off. Those FETs are on or off. You can't slow down the charging and gracefully go into something. It's on or off. And when it gets to a point where it's got a problem, it turns the battery off, and that's it. It's not part. But there is that external communication. Here's where it comes into play. Yeah, you can use your cell phone and look at what's going on, but it's also, you can connect the BMS to something like the Victron Servo, one of those things, to control your solar charger. And now the battery is a part of your charging system regulation because it's part of the overall design system. A couple of years ago, I gave a talk on my Jack solar system. Fancy presentation. I've made it better since then. I'm not going to go through this, but simplifying a couple of key pieces. The power supply, an ideal diode to prevent back feeding the power supply. There's a fuse block, 300 amp hour battery that I built from cells, and a circuit breaker in front of that, and some lows down at the bottom. And if you look at thing in use, this is one day a couple of weeks ago, I put my meter out. Everybody's got a good meter, right? You look at the voltages, and 12 gauge wire. Everybody knows 12 gauge wire is good for 20 amps, right? Yeah. House wiring, 20 amp circuit, 12 gauge wire. 14 gauge is good for 15 amps. Anyway, so I've got 12 gauge wire going from the power supply down to the terminal block. I've got, I think, 8 gauge going to the battery. I'm pulling 7 amps out of the power supply. The sun had just gone down, so the power supply is kicking in with 7 amps. Battery's feeding out 5 for a total of 180 watts going into the load. It's running a computer monitor and that kind of stuff. But look at those other numbers: 0.021, 21 millivolts of drop across about an 18-inch piece of wire. 73 millivolts between the diode and the terminal block. I'm losing a bunch of, I'm losing current here, I'm losing power, but mainly you can't tell. I mean, the curve is so flat. These millivolts make a difference. Your connections make a big difference. I have several meters with, apologies to Confucius, Ham with a meter knows what the voltage is. Ham with 2 meters is never quite sure because they're going to read a little bit different. I found 2. This is one of them. I have another one that reads, they're within about 3 millivolts of each other. So I call that my truth. Other one. Anyway, the resources online, big channel on YouTube and on the web, off-grid garage. You all know about Will Prowse and his experiments with a hacksaw and a lithium batteries. He just tears these things apart, looks inside of them. This guy does kind of the same deal with battery management systems. He's got this garage filled with these 48-volt batteries that he's powering the world with it. But he goes into what's going on behind them. 2 articles to look at. There's a video there on the settings that go into the BMS and why they're important. It's basically the information I presented today, and he's got a little more detail on his website. So with that, open it up for questions and see if you've got any comments. There's one in the back.
Can you talk briefly about that ideal diode and how that works and how to choose one?
Oh, yeah. I forget who turned me on to that. I think Greg turned me on to these things. They're used in the solar environment, solar power thing. It's basically it's like a diode, but it's a set of FETs, high power MOSFETs that are wired up such that they look like a diode to the outside world. But just like in a BMS, the voltage drop is almost nothing. It's in the millivolt range. but they act like a diode. So you put one of those between your power supply, which doesn't want to be backfed, and the circuit, or the solar panel that doesn't want to be backfed, and your other panels to keep all your power going in the wrong direction. They're like $10-20 on the online store of your preference. Little small things, no heat sink, because they don't dissipate any power.
Great presentation, Greg. Thank you. Just a couple comments. You interchanged a couple lithium and lithium iron phosphate comments. Keep in mind, those are vastly two different batteries. Lithium ion batteries can have thermal runaway.
Right.
Lithium iron phosphate cannot have, has a severely reduced chance of a thermal runaway. I've had some computer batteries that weren't working like Greg said, and I opened them up and they literally were swollen.
Yeah.
That's a battery that is looking for thermal runaway at that point.
I had a laptop that the back cover had pried itself free because of the battery.
The problem with thermal runaway, once it starts, it's going to run.
So to emphasize what Scott just said, lithium as a generic for these batteries is not enough information. Lithium iron phosphate, also known as LFP, that we're talking about today. Lithium ion oftentimes is lithium, NMC is a common car battery.
It's what's commonly in your cell phone. It's
Also lithium polymer, LiFePO, is different than lithium FePO4. That PO has nothing to do with the polymer. It's phosphorus and oxygen. It's
the
chemical
polymer
makeup.
ones, if they get punctured, they will direct short, and they will also go into thermal runaway.
Yeah. Remember those hoverboards that were catching fire?
It's hoverboards, it's some of the e-bikes, it's some of the e-scooters. But just keep in mind, vastly two different worlds.
Yeah.
And you interchanged a couple comments in there. And from an emergency response standpoint, bad news happens when you go into thermal runaway.
Throughout this presentation, whenever I talked about lithium iron, I'm talking about LFP, lithium iron phosphate. Thank you, clarifying. Other questions? Over here. And the AGC is going to kick in. Okay, go ahead.
Hi, Greg. Mike. I have two 100 amp hour lithium iron phosphate batteries that are connected in parallel.
Okay.
And I'm charging both of them with a charger that was built for one of the batteries into one battery and letting it bleed to the second one. Does that sound correct?
If they're both in parallel,
Yeah.
they'll both charge at the same time. And if they're the same manufacturer, same type of cells, you'll probably be okay. If they're wildly different, I do it. What can you get away with? You can get, if they're all lithium iron phosphate and they're all kind of about the same, you can usually charge them all in parallel and not be too far off. Some of the manufacturers do specify a maximum number of in parallel for their own reasons, and I don't know exactly why.
Okay, and if I can ask a second question. It's a 40 amp charger that's built for one of the 100 amp hour batteries.
40 amp, 100 amp hour battery is it's aggressive.
So I have a 50 amp hour battery as well that they recommend a different charger for, but
Yes, a smaller charger.
and use 40, it just shortens your battery life a little bit. What's that doing to my 50 amp hour?
The 50, if you put the 50 amp charger on the 100 amp battery, you're charging at a half C, which is about the maximum that you want to do.
The other way
You put the 50 amp charger on the 40 amp hour battery, or even the 40 amp charger on a 50 amp hour, you're above that half C, and you're going to shorten the life of it for sure. Is it going to catch fire? Probably not.
Is it going to be worth spending $75 or $100 on a,
They're cheaper than that.
are they?
I have the charger that I use at home is 4 amps. It just takes a little bit longer.
Okay.
There's because they're so efficient on charging, you don't need a big enough one to overcome the resistance inside the battery. They charge. It just takes a little longer.
Okay, perfect. Thanks very much.
Jim.
Mr. Greg, and anyone who's come to In the Shack, the second and fourth Wednesday night Zoom meetings know about this. But about a year back, I built myself sort of a double conversion UPS out of a 100 amp hour lithium iron phosphate battery. Problem is the battery never actually charges because the load is always drawing from the battery and the battery is being charged. Sometimes, depending on how much load, the charger is supplying all the power. Other times, if load comes up, then the charger is set to only output 10 amps, and then the remaining load gets supplied by the battery.
Yes, so that big hairy diagram of my shack system is exactly that situation. There's a load on it all the time, and I've got the solar, which is not enough to charge the battery up fully, or it'll support the overall system, but not on a 24-hour basis. What I do is I have the power supply adjusted so that if there's no charging like from the solar, the battery settles down to about 50%. With all those little millivolt drops and stuff in there, taken into consideration. Twice, a couple of times a year, I'll take the loads off, I'll put a little more charging on it, shove it up into that hockey stick area, let the cells balance, and then pull it back down again. If you balance it a couple of times a year, you're good. Otherwise, you can be in that middle range and it'll be fine.
If we desire to build up a 3-cell battery pack of lithium iron phosphate, what are some safety precautions that we should keep in mind?
So a 3-cell battery is only going to give you, what is that, 9 volts something? So that's what you're looking for. If the BMS will go that low, usually there are 4S is the minimum. Check to make sure the BMS can do 3 cells. That's all I would suggest. A lot of them have a range of cells, number of cells, and also different chemistries. They'll support the other chemistries as well. But make sure you match the settings. Yeah.
Yeah, I have a similar charging question to the one that came from the other side over here. That this time it's in series.
Series, okay.
So charging lithium iron phosphate batteries in series, same model, same capacity. Any concerns there? I'm using a high quality Victron lithium ion charger.
So you're taking 4 of the 12s to make a 48 volt pack?
It's a 12 volt, 10 amp hour lithium ion battery, 2 of them in series.
So to get 24 volts then?
Yes.
Okay.
Actually, you know what? No, they're in. Yeah. Parallel.
Never mind.
So let me answer the question that you didn't ask. You put them in series. So there's a lot of systems like golf carts and that kind of stuff running on 48 volts.
Yeah.
And you put these batteries in series. The problem, back to the Makita drill and your laptop, you need something to balance between the macro batteries.
Right.
The micro ones, they'll balance themselves, but between all the things in series, you need a balancer for those, and they do make those.
And the charger's not going to do that because it's only connected to each end.
Well, you got the outside edge. You need something that monitors in between, and you can find a external battery balancer. I forget what they call them now. Lead Time has one.
In parallel, I should be okay. Same model, same.
You should be good. Well, I would check to make sure that you can. I mean, for 2 of them, you're fine.
Yeah.
Typically, the minimum I've seen is like 4 as being the max.
Okay.
Some you can go 16, some you can go further than that.
Yeah, I think I've read that.
Yeah.
The other question is, you mentioned there's some margin of unsafety.
Yeah.
Connecting these batteries together. This is in my $70,000 truck, 24/7. Should I be concerned?
If so, with what area do you think you're pushing your luck?
Insurance. I'm trying to explain why it's a molten pile of plastic.
Yeah.
I don't want to lose it. And
No, right.
I have it connected up. It's always connected up. I run it until it runs out, and then I charge it up and throw it back in.
So if you're running it until it gets a low voltage disconnect, you're flirting with that lower bound, and that's not good. If you run it down to like 20% or something, and then charge it back up, you're fine. That's what that's a big advantage of lithium in general, is that they could take that wide swing, where lead acid, if you go below 50%, you're starting to damage it.
Beautiful. But thank you. I'm aware of the cold issues with
Right.
lithium ion, so I pull it out in the winter. I don't typically use it unless I'm in the car. But what about the summer? In the heat of the car, out in the sun, is that something I need to worry about? Should I be pulling it out then too?
Any battery, anything chemical, hot is not a good thing for it, even electronics. So yeah, look at the specs. All the lithium that I've got is indoors or in protected areas.
A lot of these cars have batteries now in the passenger compartment.
Oh, yeah.
I do have,
If you look at my ham shack,
Yeah.
I'm sitting at my desk. Right there is my 300 amp hour lithium battery that I built.
right,
I have no concern.
right.
What's inside your house?
What's here inside the house?
And it's inside the house, yes. But I'm sitting right next to this thing. Now, I'm not worried about it.
Thank you.
The lithium iron phosphate chemistry, you have to work at it to make it do bad things. So that was Scott's point. As long as you don't push the bounds on the disconnects, the low voltage or the high voltage, if you stay in that section in the middle. And the 20 to 80 is also not a requirement. But you can go down, you can go down 10 up to 100. It doesn't care that you have to leave it at 100%. But stay away from the bottom end and don't push the high end.
Okay, thank you very much.
All right, thank you very much.